Hi, I'm Mohammed Sadri, and the title of this video is Partial Reconfiguration for ZYNQ Ultrascale Plus. Xilinx is trying to change the name of partial reconfiguration to Dynamic Function Exchange. This video is a hobby video, doesn't have anything to do with Xilinx. I don't guarantee the correctness of what I say in the video, but I create projects and I develop software and I try it on the board, and we will see that the ideas work fine. Before I continue, I should mention that this video is in parts supported by Blickfeld GmbH company. It's a company creating LiDARs here in Munich. The LiDARs are low cost, accurate, they are ready to be purchased, and they have a very nice software interface. You can talk to the LiDAR, configure it, use it, acquire point cloud very easily. Also, the company is hiring. So if you're a developer and you like this sort of tasks, then maybe if you like, you can have a look at the website. This series of videos have the following agenda. First of all, this video is introduction. The next video will be about the Vivado project, and then the next video would be about the standalone software, and the final video about Linux software. As of the time I'm recording this video, I'm still working on some parts of the software. What is partial reconfiguration? Or let's say dynamic function exchange. What's dynamic function exchange? Here, what I'm showing you is basically the layout of ZYNQ Ultrascale Plus device. Here is the PS, and this area here is the PL. When the device comes up, usually the PS, the CPU here, reads a bit stream from outside and programs the PL, the FPGA part, with that bit stream. Now, in previous videos, I showed you that the bit stream with which we program here, the PL, this can be changed, this can be updated. So we can reprogram the PL completely during the course of FPGA operation. But sometimes this is not what we want. Sometimes we want to keep some blocks operating on our FPGA and change the function of some other blocks. Basically, the function of these blocks, I want to be able to dynamically change them during the course of operation of the FPGA without changing the function of other blocks. This is where partial reconfiguration becomes handy. Why do people do partial reconfiguration? One big reason is area. So in the projects I have done, I have seen people usually use partial reconfiguration when they see that they have the FPGA area completely full with different functions, but they need to push more functions inside the programmable logic. What they usually do is they sit and analyze which blocks are not needed at the same time, and they have kind of similar area. Then what they do, they take a piece of the silicon, they take a piece of their programmable fabric, and then each time they partially reconfigure that area with the function that they need. For example, here, imagine module 1 is talking to the rest of the logic. It receives some data from the rest of the logic, passes that to module 2, gets the result back, and then passes the result to module 3 and gets the result back. The fact is that module 2 and 3, they are not needed at the same time. So what we can do is we can take that area of silicon in which module 2 is residing and reprogram that area when we need with the logic of module 3. Of course, there are some constraints, but the general idea should work. So we partially reconfigure this piece of silicon with either the logic from module 2 or module 3 based on the functionality that we need now. This way we are saving some area. What other reasons are for partial reconfiguration? When you want to have an adaptable hardware, basically you have a software that's operating, you have a software interface, and the software interface is responsible for collecting data from somewhere, passing the data to your FPGA, which is acting as the hardware accelerator and collecting the result. And then on your FPGA, on your hardware accelerator, based on the user requirements, you want to have different operations. Then partial reconfiguration will become handy. For example, here I have this DMA engine. The DMA engine is responsible for fetching data from DRAM, passing data to the accelerator, and collecting the result backs and putting the results in the DRAM. And then I have a software running on the CPU which manages this DMA engine. Now, based on the requirement, based on the type of calculation that the customer wants to do, I want to be able to basically reconfigure this hardware accelerator with different source of logic so that I do that different source of mass. Or here I have a network interface. There's a software sitting somewhere on the network. This software is responsible for passing data over this network interface to the hardware accelerator and collecting the result. And then I want to be able to, based on the requirements that the customer has, the user has, I want to be able to reconfigure my programmable fabric to do different type of calculations that the user needs. So basically, I want to have a hardware which adapts to the requirements of the user. What other reasons are for partial reconfiguration? There are some other reasons. For example, here we have a hardware accelerator which is being used for some sort of security function. It calculates a cipher, and then I don't want this guy to be present in the programmable fabric all the time. I'm worried about this guy. I want to have this guy in the programmable fabric only and only when needed. Other times I want to have this area being completely clean or having a dummy logic. So what I will do is I partially reconfigure this area of the FPGA whenever I need to calculate the cipher. For example, I have a encrypted bit stream for this hardware accelerator. Using that encrypted bit stream, I only reconfigure the FPGA when I want to calculate the cipher, and other times I reconfigure the FPGA in this area to have a dummy accelerator which does nothing. This way I feel more confident with my hardware accelerator. I feel more confident because it's not always present in the hardware. It's only and only present when I need it, and other times it fades away. Or imagine I have an accelerator, and this is the sort of calculation that this guy does is extremely important for me. For example, it's controlling let's say a medical device, a life supporting medical device, and it's extremely important for me to be sure that it's always operating correctly. It's important for me to know that whatever I have configured, the structure of this programmable logic that I have here doesn't change. No bits flip. The radiation, for example, has no effect on it. Then what I would do, I reconfigure this piece of silicon every while or so. For example, I reconfigure this piece of silicon every 100 milliseconds. Just to be sure that what I have here is exactly the bit stream I want. Nothing has changed. Then again, partial reconfiguration becomes very handy. There are many examples for partial reconfiguration. These were just a few. Now, partial reconfiguration is nothing special. People from 10 years ago, they have been doing partial reconfiguration. If you do a very simple search in Google, you can see people have been using Xilinx devices for partial reconfiguration back then. But still, it's a very hot topic. Still, it's evolving. If you look at the Vivado tool, you can still see the tool is evolving. With every new version, partial reconfiguration flow is becoming easier and easier. Why? Because it's heavily used in different fields, in the industry, in telecommunications. Many people, they use partial reconfiguration. Here I have put another example, which is happening actually a lot of times in our world, and it's happening more and more and more every day. FPGA boards, they are opening their ways to cloud computing. Basically, if you look at one of these server farms, you can see every day there are more and more FPGA boards being added as hardware accelerators to these farms, and they will be used by customers so that they can accelerate the type of calculation that they want to do. If you look at the FPGA, usually it has a set of logic which are constant, they don't change, and they are out of the hands of the customer. For example, some housekeeping logic, PCI Express interface, DRAM controller. These are sort of logic which are programmed by the cloud provider. They don't change and the customer cannot change them. Basically, the customer doesn't want to change them. He doesn't need to. But the rest of the programmable fabric is available for the customer, and the customer can put his set of different functions on this programmable fabric so that it can accelerate the type of processing task that he has. And this is where partial reconfiguration becomes very handy. Basically, you keep these areas of logic, you don't touch them, you reconfigure only those areas in which you want to implement your own function. And then the function will be exchanged dynamically through the course of operation of the system based on the requirement that the customer has. So you see how important it is to make partial reconfiguration as simple as possible and to have like easy to use software for partial reconfiguration. And this is what's happening today. So in these videos, I'm trying to basically address partial reconfiguration through PCAP and through ICAP, through both of these interfaces. PCAP is basically the interface that the processing system uses to configure the PL. ICAP is the interface that can be used by other means to configure the PL. For example, in the design that we are providing, we have the DFX controller IP core of Xilinx. We have connected the DFX controller to the ICAP. The DFX controller will be responsible for reading the partial bit streams from the DRAM and passing the partial bit streams to the ICAP. The ICAP then configures that area of the logic that we want, that's mentioned by the bit stream. The same operation can be done through PCAP. Basically, the software that we are running here on the CPU can load the partial bit stream, can obtain the pointer to the partial bit stream, can configure the PCAP and the related DMA engine so that the bit stream gets given to the PCAP and then the PCAP programs the FPGA logic. So the same operation can be done through each of these interfaces, and we try to study and to show both of the interfaces. Sometimes I have the feeling that partial reconfiguration through DFX controller and ICAP can be more versatile. The DFX controller contains this XI master interface through which he can himself directly go and grab the partial bit stream from the DRAM and give the partial bit stream to ICAP. So when a hardware trigger comes and you want to do the partial reconfiguration as fast as possible, DFX controller can have a lower latency compared to other software-based solution. The board that we use for these videos is ZYNQ 104. We use Vivado 2020.1, Xilinx 2020.1, and the entire software is running on Ubuntu 20 LTS. These reference documents are used for these videos. Basically, you can refer to them to learn more about partial reconfiguration flow. And this is the folder structure of the deliverable coming with these videos, which contains the main Vivado project, main Vitis project, C source codes written for doing partial reconfiguration, TCL scripts to create the Vivado project and to create the IPs, shell scripts to run the whole flow, RTL that we need for partial reconfiguration flow, the RTL for top level, the Xilinx project, the IPs that we use for our example Vivado design, the generated hardware definition file, the constraints, these videos, and the presentation that you are seeing right now. All of them are in this deliverable. Now here is a very simple block diagram representation of Vivado project that we use as an example. In this Vivado project, we have basically 3 configurable regions. And in each of the configurable regions, we have basically a hardware accelerator. This guy is responsible for receiving data as a stream and then perform a sort of processing on the data and giving the result back. The same is true for this one, for Reconfigure region 3, but then the Reconfigure region 2, it doesn't have these XI stream interfaces. It has an XI slave interface, memory mapped interface. Now, I have implemented simple functions for each of these blocks. And then I can dynamically change the function for each block. For configure region 1, I have implemented 2 functions. Either it can be reconfigured to perform multiply tasks on the data stream which is coming, or it can be reconfigured to perform power. The next reconfigurable region, either it can be reconfigured to calculate the reciprocal of the stream of the numbers in the stream that it receives, or it can be reconfigured to calculate natural logarithm. And then for the final configurable region, either it can be reconfigured to have a simple block with XI light interface, which whenever you read it, it counts by 1, or it can be reconfigured to have a block which counts by 5 whenever you read it. So as you see, the Vivado exam project is simple, but it shows the partial reconfiguration flow completely, and also using this Vivado project we have developed, basically it's done, a complete software which can show the partial reconfiguration and how the function of each of these blocks dynamically changes. Then also in our Vivado project, we have the DFX controller, which is connected to ICAP, and this is another path that we try to reconfigure the blocks using it. So we have the standalone software, which configures and runs the DMAs, perform partial reconfiguration using ZYNQ FPGA, and configures and runs the DFX controller. And then finally, we have the Linux software, which uses FPGA manager to perform partial reconfiguration. And then also we, at the end, develop a kernel level driver for the DFX controller. So this is the end of this video. We go ahead with the next video, description of the Vivado project. Thanks for watching.